For semiconductor materials, the number of charge carriers is not the full picture. For semiconductor material, the available energy states are also the 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 other very important part of it. So we may have a bunch of electrons, but unless we have the available energy sites in the conduction bands, so those electrons can jump and take up those energy states, there's no conductivity, there's no conduction. So hence, we need to know how many charge carriers are there and how many states are there that they can occupy. Now these states or number of states are something which is a probability function. And probability again is something which tells us the chances of having something, right? So for example, we flip a coin. One flip of coin, the probability of head is half, probability of tail is half. Now, if I use 2 coins, the probability of 2 tails is 1/4, probability of, the probability reduces as we increase the number of coins. So now here, when we talk about the possibility of an electron to jump and find an empty state, those empty states need to be understood in terms of probability function. So the line where it says electrons and solids obey Fermi direct statistics, Fermi direct were 2 scientists who came up an equation of statistical function which tells us how many states are there or gives us an idea of how many available states are there. So don't get scared when I show you the next slide, because this slide is nothing but taking care of these things, the available or distribution of electrons over range of these electronic states, right? So we say it's a statistical argument which tells us electrons over where they can fall. And that equation is this. So what it is, this equation is a statistical equation. Fe equals 1/1 plus exponential of E minus Ef over kT. Let me break it down. First of all, there's K is Boltzmann constant, T is temperature. At room temperature, kT is a well-defined number. We have a number for kT. We'll look at that later on. So what is here? There are 2 things. There's f of E, which is a distribution function, which will tell us what is the probability of what is the probability for an electron to find an available location. So in the development of this equation, we take these things into account. The indistinguishability of electrons, which means that when there are 10⁻10 atoms, for example, they all are sharing electrons with each other. They're all sharing holes with each other, which means one electron we cannot pick and say, okay, this belongs to this atom. They'll belong to every atom that's there because they are so close. The other thing is the wave particle duality and Pauli exclusion principle, which we saw before. So these things are now packaged together into what we call the Fermi level. And what it does is, taking in account of those things, it gives us the distribution of electrons over a range of energy states. Now, E here is the energy state. So E would be what would tell you that if there's conduction band and you go above, the energy increases. What is the chance of having a free energy state? Now, what is EF? Now, EF is something which requires its own understanding of what is that level. So let me go to, so EF is a level where you have equal number of electrons and equal number of holes. It means that above this level, you will have all electrons. Below this level, you will have all holes. So it's a number right in the middle, just the half probability. That's what we call as EF. Right? We'll come back to this, but just wanted to say that EF is an energy level, which tells us that at that level, it's the half probability of having a energy state for electron or not. So if you go above it, the probability of having a state increases dramatically. If you go below, probability of finding a state reduces dramatically. So we use that number to just define a half state or half situation. Now, so this function will tell us that in energy state E, what is the probability of finding an electron there? This is what this relationship is all about. And EF is we call it Fermi level, and it represents this quantity that helps us analyze the semiconductor behavior and tells us if there is an available energy state or not, right? Now, when we talk about these states and we talk about the number of electrons, these in combination will tell us how much conductivity or how good a conductor a semiconductor would be based on the value of the Fermi level. So this is an important factor that if when an electron jumps from valence band to conduction band, it's going to higher energy level and it has to find a space to fill it. Now, what is that energy level? When you go back, think about Bohr's model, we calculated that energy level, right? But now we have this multiple levels, multiple ends, and that's where we need to know that which energy state that electron will occupy, which level, the level that an electron occupies will help us finding the conductivity of that material. Now, when at 0 degree Kelvin, absolute zero, there is no electron in conduction band. All electrons are very rigidly stuck in valence band. There's nothing above. So the probability of finding above Fermi level is 0, right? But when we increase the temperature higher than 0 degree Kelvin, the probability of finding these filled states in conduction band start increasing. That's what KT in that exponential denominator is about. So temperature goes up, the Fermi, the probability goes up. The statistical probability of finding an electron goes up. So that's what T does there. And the function would be a step function, which means everything filled below Fermi level, everything empty above Fermi level. I just got a message, participants can see my application. Did something change in Zoom on your end?
I don't think so, sir.
Okay, Zoom send me a message, something. Now, if the above is all empty, how does that change? So that changes when temperature starts cranking up. And that's what we see here from that step function. As T goes up, the probability on both sides getting skewed, which means the total probability is always going to be 1, right? So total is always, so if there is more probability on the upper side, the probability needs to goes down on the lower side. And if you think about it, if electron jumps from valence band, it has to leave some spaces below. So the probability of finding that electron in valence band is now going down because the probability of finding it in conduction band is going up. This is all it says, right? With me on this, if we get this hammered up, the rest of the things become easy for us. that what does Fermi function or Fermi level mean here. Now, there is, so as things keep on going up, and this is from the book, there is, which means now there are more available states above Fermi level, which means now there is more possibility of finding electrons in those places. And this is all it says, right? Now, the Fermi level EF for an intrinsic semiconductor material where there is equal number of holes than the electrons, equal number of holes in valence band, then the number of electrons in conduction band. So if you think about it, then the EF or Fermi level should fall right in the middle of the band gap. So and that's actually the case. So when we plot Fermi level for intrinsic semiconductor material, intrinsic means equal holes and equal electrons, we make it right in the middle. So we call it EI. We'll talk about that also soon, very soon. But now I say, let's switch it 90 degrees. So right now, if it is filled like this, but we always think of valence band at below and conduction band above. So right now it's showing conduction band on this side and valence band on this side. Let's switch it like this. So we follow the band gap, the way we show band gap. So it would be now like this, where at 0 degree Kelvin, it's still showing slightly above 0 degree Kelvin because you see some holes are there in valence band. But at 0 degree or equal number of electrons holes, this function would be, yeah, so it's not a step function. Now the function is slightly skewed, which accounts for those few electrons that are jumped and gone to conduction band. So this picture is slightly above 0 degree Kelvin. We all understand this? So far with me, Giselle, does it make sense?
Yes, sir. Yeah.
But few people I can see, Daniel, Manuel, does it make sense? Now, if you get many more electrons in conduction band, this whole function will move up, which means it will give more probability on the conduction band and less probability in the valence band for electrons, right? So we're just talking about electrons right now. But there is a similar function that exists for holes as well. So now if you look at that small portion in the conduction band, it's going to increase if I get more electrons in conduction, which means that thin part is going to go fat now, right? So now, which means the Fermi level is going to move up, so it can increase more probability of finding more states in conduction band. All right, so now it means if you make a band diagram and if you make a Fermi level close to conduction band, what kind of semiconductor material will be that? I threw a spanner here in the moving machine. So if I make a band diagram and my Fermi level is close to conduction band, what kind of semiconductor material could be that? It would be N-type because it will have many more electrons in it. The Fermi level close to conduction band would be, like we are showing here, would mean many more electrons in conduction band, which means N-type. And if the Fermi level is close to valence band, that would mean many more holes are there. That would mean it's P-type. But we'll see. This is something. Now, probability is something where if you define probability of one type of event, the other type of event can be written as 1 minus the other guy. So for example, if I were to write, let's think about two coins, two flipping coins. So if I flip two coins and I say the probability of finding 2 head is 1/4, then the probability of all other events is just 1 minus 1/4, right? Which will be 3/4. Right? So if we define the probability of electrons as f of as E of C, we can write the probability of holes as just 1 minus E of C. That's all it is showing in this picture. That what we have done is we have just added pointer. Where is the pointer? These are pointer. So what we have done is, if the probability of finding something was this, or the conduction band, the probability of finding holes would be just 1 minus that probability. You with me on this?
Yes, sir.
All right. So because now that's what we're going to do. We're going to write equations for electrons, and we're just going to, when we write holes, we're just going to write 1 minus E of C for holes. So don't get worried that, oh, why is 1 minus F of C. So now if you bring those animations together on one slide, which is your figure 315 from the book. So in n-type material, there is a high concentration of electrons in the conduction band compared to the whole concentration in the valence band, right? So that's an n-type material. In this case, the distribution function f of E is above the intrinsic level, which was the middle level, which is the blue line, which is written there in figure A, intrinsic. Now going to figure B. So this level was right in the middle. But now when we go to B, where there are more electrons, this EF is moved up close to conduction band. Now, the distribution function is keeping its shape, right? The distribution function is, remember, it's dependent on temperature. Or later on, we'll see that when we do extrinsic, then you have increased electrons anyway, so then it's going to move up automatically because of too many electrons in there. Now, the shape of function stays the same, but because it moves up, it gives you much more distribution or much more probability of finding electrons there. Now, the larger concentration of electrons at EC and N-type, that implies a smaller number of holes in EV. So which means that this function, when it has moved up, it has made the distribution in valence band much more narrower, which means fewer electrons there. Now, when we talk about this in terms of holes, then we take that EC function and we write down in terms of EV, right? So we're just saying that the level in the conduction band is now much thinner. Sorry, in valence band is much thinner than conduction band. So on that side, then we take the, all right. So another thing, now to find the difference of E minus EF is something that we can plug in into that Fermi function that we wrote in just generic terms, where we wrote just E here. So then this function for EC is where then we will write this guy as EC and not just E, because this is above. But when we'll write EV, then we will write EF minus EV, because the energy level of valence band is lower than that. So here we can see energy levels EC minus EF or EF minus EV because of the difference. So what we have to use is to find the difference of two energy levels. All right, so where does it help us? So, okay, big deal. We said, okay, total number of electrons and total number of energy, available energy sites. Or we said total number of holes and the probability of empty sites for holes. this can give us exact number of electrons and holes at equilibrium. So what we do is we take the distribution function, we play it with it, and we can calculate n naught. So taking reshuffling, we get this equation. Don't get scared. I'll just break it down for you what's in there. So what it has is NED is the density of states. It's the number of states per centimeter cube in the energy range DE. And we break down NE also. There's a formula for that. Probably next slide it will be there. So what we are doing here is we are using the Fermi distribution function to calculate the concentration of electrons and holes in a semiconductor. If the density of states in valence band and conduction band are known, and they are known by this relationship. At the lower level, this NC equal to 2 pi Mn star KT over H. Everything is known. You know pi Mn star is effective mass for electrons. We know mass in free space, but when we talk about semiconductors, the mass is slightly different. We call it effective mass. We know effective mass for electrons and holes both. Here we are talking about electrons. K is Boltzmann constant. T is the temperature, and H is the same guy, what we are using before. What do we call it? I'm forgetting the constant. What is H? And we use H and H bar both. The guy who did the photoelectric experiment.
Isn't that Planck's constant?
Planck's constant. Yeah, thank you. I'm talking too much today. So NC is a known quantity. We know exactly how many density, what's the density of states. So we plug into this relationship, we can find concentrate N naught. N naught is the concentration of electrons at equilibrium. So wherever you see subscript 0 with electrons and holes, it just means equilibrium conditions. Equilibrium means they're stable. No, nothing is changing. We are not adding anything, or there's no excitation happening. System is stable. So N naught is the equilibrium concentration of electrons. Now, what this relationship is telling us is it's saying that from the edge of conduction band out to the infinity, all the energy levels above conduction band, we are integrating the states, density of states, and the function related to energy, probability of occupancy, which is F of E. We integrate, it gives us exact number of electrons per unit volume there from conduction band to infinity. So this is the total electron concentration integrated over the entire conduction band, right? So this comes from the function NC. Now when we integrate, we get a much simpler function, which is NC F of EC. They both are known. We know NC and we can find F of EC. We know the location of EC, and that will tell us where it is located. Now, the density of states is something which increase in the conduction band as we go above the conduction band. Just above it increases. On the other hand, as we keep on going up, and for large energies, it goes down. So which means electrons are located at energy levels which are very close to conduction band. So we don't use higher energy levels. They are always going to be, they're going to release energy and come back to lower energy levels. And the result is that this function, the product F of E NC and F of EC, it decreases rapidly above conduction band. So very few electrons would be in the energy states which are too far away from the conduction band edge. In the same way, the probability of finding an empty state or hole in the valence band, 1 minus f of e, is the same way. They occupy all the states which are very close to the valence band, and they would fall off because the number of density of states would fall off at higher energy states. Now, where does it lead us? It leads us that if electrons are more, density state in valence band would reduce. In a similar way, if holes are more, density of states would increase in the valence band and go down in the conduction band. And from simplifying that original relationship in terms of conduction band, we use now EC instead of just E. Now here, the integration and playing with the holes, we can get the density of states at EC by simplifying. Why? The exponential function is too large than number 1. When that happens, you can simplify and remove, ignore 1, which results into you can just bring it up with negative sign in the exponential. Now, in this case, there are a few assumptions that go. One is that the KT, in the exponential power, it is much larger than the value of EC. So the exponential term is large now with respect to the unity, and thus we can simplify in this way. Now, KT, what is the value of KT? KT is something which you'll remember. We call it 26 millivolt. It's a constant. Wherever you see KT, we will use it as 26 millivolt. Let me write down here a second. I'm using now 2 things. Or then we can write it 0.026 volt. Sorry, it's electron volt. It's not just volt. So wherever you see, this is at room temperature, it's a constant. So when we have the KT value known, we can, from this, the relationship which is in circle, we can find out exactly what is the number of electron at equilibrium. So it's an exact science. When you use a device, when you use a semiconductor material, we know exactly how many electrons are there. If you know that, then you know what kind of conductivity or what kind of charge or current we're going to get from those devices. All right. So, and again, density of states is NC. All the values are known in that, which gives us the exact number of density of states. Now, similar argument for concentration of holes, but now what we are using is we are using the energy level at valence band. So hence, instead of EC, we are using EV. We do the same thing, but here now we are taking the subtraction, 1 minus the probability function, using the same argument as we were talking about 2 coins and the flip of coins, and 1 minus the probability of the event. So we know the probability of EC. We want to find the probability of the other event. We just take 1 minus the probability that we have for conduction band. So by this, we can find the concentration of holes in the valence band. And NV here is now the effective density of states in the valence band. So here now we are using the MP star. We are using the effective mass of holes, not for electrons. So from using the effective density of states in the valence band, we can now find the exact number of holes at equilibrium in a semiconductor material. Now, what does that mean? It means that we can solve the homework problems that are assigned this week. So it means that if you are given some information about the doping concentration, we can always find how many electrons and how many holes are there. So next slide is very important because this lays down a bunch of important information. The information is that we talked about at equilibrium, we said N naught or P naught, which meant that it could have been doped. But if it is not doped, we are just using intrinsic carrier concentration. And intrinsic carrier concentration means P is equal to N, right? We all agree on that. It means in an intrinsic material, all the electrons in the conduction band are coming from the valence band and not for impurity. And so that's there's same number of electrons and same number of holes. So here it's the same relationship, but what we have done is instead of writing EF, we are using EI. Can see that first relationship? Is it big enough to see or should I zoom it in? Can you see the first relationship here?
Yes. I guess I missed out on a YI.
YI?
Yes, as in why is it I instead of a F?
That's what I was going to explain. So now we were talking about conduction band and valence band, and we said, okay, there's more holes. We call it EC. Sorry, EF. Right? So we said, okay, it's moving up and down because the number of electrons and holes are changing. But if you remember the first guy, which we said, for example, in this case, not in this case, sorry. So this has to go, again, this one, where the conduction band, where the electrons and holes are exactly equal. So in this case, where is the Fermi level? If you can just eyeball, what's the location of Fermi level with respect to conduction band and valence band? So if you look at conduction band, you can eyeball. Where do you see? Is it close to conduction band or close to valence band? Or it's right in the middle?
Right in the middle.
Right in the middle. That's the answer. So it's the intrinsic situation when it is right in the middle. And when it is right in the middle, we can call it EI. Subscript I. Which means that instead of writing EF, we can just write it as EI. It's right in the middle. Which means, we know band gap of all materials, right? So EI is always going to be half of band gap. So whenever we are dealing with the intrinsic material, we can always calculate it by what is band gap? EG divided by 2. That's going to be my intrinsic concentration, intrinsic level of Fermi level, intrinsic energy of Fermi level. All right, with me on this? Now I take you to this guy and I say, what we are doing here is, not this guy, the next guy. What we are doing, let me clean my slate. What we are doing here is, we are doing nothing but we are using that intrinsic value of EF here. Same relationship, but now we know its value is right in the middle. So both relationship. This is one thing. The other thing we said, okay, in intrinsic, Ni is equal to Np. Ni is equal to Pi. Now here, subscript I means intrinsic levels, right? 0 or N subscript 0 was for equilibrium. And equilibrium could have been in intrinsic or in an extrinsic both. But now here we are talking specifically intrinsic semiconductor. So if they're equal, we can equate them. This is what we did. And what you get is you play with this and you get this relationship with them, which is nothing but a fine constant for us, where we say the product of equilibrium electron concentration and equilibrium hole concentration is always going to be the square of intrinsic concentration of electron or hole. Both should work here. So I might as well write pi square as well, because ni and pi are same, right? With me on this?
Yes, sir. I just also wanted to make sure, essentially, since NC and NV, uh, all the values are always known, would that just essentially make it a constant itself?
So NC, yeah, for a given temperature, yeah, NC and NV are constant for a given
Yes,
temperature.
for the purpose of our class, because I know that the temperature will
Right.
definitely range, but everything
Right.
in real life applications.
So this is what it is. So it's always going to be a constant. So which means for a given material, density of states are known. But how many are filled is a function of level of Fermi level, the value of Fermi level. Is it up than intrinsic level or below than intrinsic? If it is above intrinsic level, it's an N-type material. If it's below intrinsic level, it's P-type material, right? Many more electrons than holes, many more holes than electrons. My office background is probably not letting my hand show up. All right. So now if we, let me clean the slate again. So now, okay, what does it mean? It means if you are given a problem statement where you are given the doping, N-type doping, from just N-type doping, we can find out everything else, because Ni for every material is known. For silicon, Ni is, all right, so this, you have to remember this forever and ever and ever. For this course at least. So Ni, where's my writing thing? All right. For Ni, this, that. Instead of drawing, let me write it down. Ni for silicon is, for example, 1.5 times 10 raised to power, where's the count? 10 raised to power 10 per centimeter cube. Always. So if you know Ni, and if you are given one kind of charge concentration, for example, N naught is given, you can always find P naught from there using this relationship. I lose my, so we can always use this relationship to find, if we are given electron concentration, we can find hole concentration. If we are given one or the other. If we are given the level of Fermi level, we can find the carrier concentration from that. If we are given carrier concentration, we can find the level of Fermi level. With me on this? This is known for every material. This is known for every material. It's just half a band gap, right? This is constant 26 milli electron volt. I'll say millivolt, but that's milli electron volt. So we are always going to use this fundamental relation to find any one thing is given, we can find everything else. With me on this?
Yes, sir.
So what does it mean? It means that we can find exact carrier concentration just if we know Fermi level, for example. Now, this is just summing it all up. When we make band diagram, so we will always write one more thing. So we used to write EC and EV. Now we will write EF as well, always. EF for intrinsic material would be right in the middle. Now, I say intrinsic material, but just few minutes ago, I said that we can dope the N-type and P-type, both of those, right? So if you dope a material with equal amount of N and equal amount of P, where would be your Fermi level?
In the middle.
Again in the middle, right? Exactly. So although it's not an intrinsic material now, but because the doping is equal, so they're compensating each other, it's going to stay in the middle. But if it's an N-type, EF will be always close to EC. If it is P-type, EF will always be close to EV. So the leftmost picture is the most, what you have to remember for sure. These ones are what will tell you about the density of states. This will tell you about the Fermi Dirac distribution. And this is the way how you can show relative amount of carrier concentration, not exact, but relative amount, right? So it all comes together with density of states, with the Fermi function, with the resulting number of electrons and holes in those states, and the thermal and the Fermi Dirac distribution, F of E. Right? So now if I'm equipped with this information, I can go back to something which I skipped before when we are talking about the extrinsic semiconductor materials. And that was that when we dope it, the doping would result into location of my Fermi level. So for example, P-type, we'll put this line close to EV. So if I give you group 3, I just say group 3, or I give you an element for group 3. You should know how to draw the band diagram. And why I would just give you these, because they're not too many. You have to remember 3 from group 5 given here and 3 from group 3. Boron, gallium, and the most commonly used dopants, right? So from this, then we can draw our band diagram. In this case, with N-type, EF is shown close to EC. Bring it all together. This is just telling us where to draw my Fermi level when I have the band diagram for a material. All right, so this is just summing up for electrons. This summing up for holes, same information, and this is now showing us few examples where the Fermi level would be located for one material versus other. So one thing you can see is the Fermi level is not changing, the bands of materials are changing. For insulator, they are splitting half and half. Again, because the intrinsic Fermi level is always right in the middle. So insulator is a large band gap, Fermi level is still in the middle. For the middle case, semiconductor, Fermi level is still in the middle, and we know the band gaps of all the materials, which means we would know the location of intrinsic Fermi level, Eg by 2. Similar case for conductors, where it's right in the middle and there's no problem for electrons to jump up or down. Now, intrinsic semiconductors, we did this before as well. So what we are doing is these relationships can help us deal going from intrinsic levels to find the equilibrium concentration of electrons and holes. Always remember, I substrate means intrinsic value, which is a constant, which we know for every material, 0, naught, O, whatever you call. Substrate means equilibrium value, which is the value that we get after the material has been doped. And that can be found in terms of the intrinsic value and in terms of the difference between the bands, in the difference between the conduction band energy value and the Fermi level energy value, right? KT is known, everything else is known. And that can tell us exactly how much are the charge carriers in there. And this is, there's an, of course, there's homework I'm assigning this week, and there's a quiz also, but let's look at an example from the book. I told you silicon intrinsic carrier concentration is known, 1.5, 10 to 10. The question is, silicon sample is doped with arsenic atoms per centimeter cube. What is the equilibrium hole concentration P naught? So there are two clues here about what type of dopant is arsenic. When they're saying what's the equilibrium hole concentration, which means this is N type. So we know N naught. Now we have to find P naught. That's number one. The other question is where is EF relative to EI, right? We know the band gap. We will find the value of EF and we will find the difference of those two, and that will tell us where is EF relative to EI. Are you with me on how we would do that? It's from right from the book. What's happening here is we take the value 10 raised to the power 17, we put it in, plug it in. This is the relationship we just saw. We know intrinsic level, we know the equilibrium level because that's given to us. We can find out the value of number of holes in that semiconductor. And now we flip that exponential relationship, we bring everything to the other side. We know everything on this side now. We know N naught, we know Ni, we know constant N naught is given. KT we know 26, it's 0.0259 to be more exact, 26 millielectron volt. And that tells us the energy difference between these two in electron volts. Are you scared of this relationship? So this is the, I would say, the fundamental relationship to find carrier concentration in semiconductor materials. It's from the book. The example is right from the book, 3.5. All right, questions. Couple of more things. Carrier concentration has a dependence on temperature. So it's relatively straightforward. When we bring those two relationships together, we see that there is time, this temperature relationship, which we see, temperature shows up at two places. One, it shows as direct dependence, and then it shows as negative exponential dependence. So it's not very straightforward, but when you plot it, we see that with temperature, this is temperature going down from left to right, which means it's increasing on this side, which means that, hold on, let me clean everything this. So temperature is increasing on this side, which means that at higher temperature, the carrier concentrations go up. But we use room temperature, which is this guy, 300 degree Kelvin. So we use these numbers for our calculations. For silicon, germanium, gallium arsenide, these numbers are given. They're given in an appendix as well at the end. Intrinsic carrier concentration dependence on temperature. But the temperature dependence of electrons and holes that are doped is slightly different, and that's shown by this relationship, which now shows that there are three parts to it. At lower temperature, it's just the intrinsic carrier concentration that's important. But then extrinsic carrier concentration becomes more prominent at higher temperature. Sorry, no, this is also where temperature is going high to the left. It is increasing on this side. This is 1000 over T. So it depends exponentially on temperature. So at low temperature, all donors are ionized, positive and negatively charged, whatever their shape is, whatever their what do you call the molarity is. If they are from the plus, which 5 or 3, depending on whatever their contribution is. So as the temperature increases, we have the intrinsic, at room temperature, we have extrinsic charge carriers. When we heat it up too much, intrinsic concentration is what takes up. So that's the dependence on temperature, but we will use 300 degree Kelvin for this course. I just wanted to show that there's dependence, which is slightly more complicated than intrinsic concentration. All right.